Okay, we are moving on to the last section in our exponent unit, and we are going to apply our knowledge now of exponential functions and connect it with exponential growth and exponential decay. Growth looks like you're increasing. Decay means you're getting smaller as you go left to right. Growth, you're getting bigger as you go left to right. Your learning target today, you can identify exponential growth and decay and analyze and apply the formula. Okay? The formula is nothing new. Look at right here. I'm just kind of scooting down to the bottom. It's the exponential function formula you had yesterday, where y equals a times b to the x. Notice x is the exponent. It has to be the exponent. If x is not the exponent, it's not exponential growth. A is the initial amount. And this is in that table. This is in your table on your notes. If you just look at this. You can maybe cloud, I don't know, whatever's going to make your eyes be able to be, this is how I analyze this. A is where you start. B is the base, which is bigger than 1. That's a growth factor. This is for exponential growth. Okay, it's bigger than 1. And x is an exponent. The initial amount, again, is when x equals 0. That's where we start. Initial, obviously, where you start. Let's give it an example. Okay, so since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, $360 billion was spent at restaurants. If this trend continues, how much will be spent at restaurants in 2015? I do want to read through this definition because it's really important. You need to know what a growth factor is. So A is the initial amount. B is also called the growth factor. It's the relationship of how things are growing. Here, it's 7%. But you don't put 7% as the B. There's a different thing. So I do need you to know that that B value is the growth factor. And notice, I'm going to highlight it. Okay. Now let me read what I highlighted there. It says the base B, that's what we just identified as the growth factor, which equals 1 plus the percent rate of change expressed as a decimal. So B equals 1 plus your rate of change. If you're growing, you're adding to 100, 1 means 100%. You're already at the 100%. You're getting bigger than 100%. 100% is like where you started. Okay, so I need to create an equation. So y equals a times b to the x. A is the initial, so let me identify. What did I start at? What did I start at? What's my initial? In 2005, about 360 billion. So my answer is going to be represented in billions of dollars. I'm not going to put all those zeros in, okay? My answer will be in billions. B is my growth factor. Now, according to how we calculate a growth factor, my growth factor is 7%, but B is 1 plus your rate of change. So my B is 1 plus 0.07. It says that you have to write it as a decimal. You have to. So 7% is 0.07 as a decimal. And now I can go ahead and plug that in to create my equation. Y equals 360 times, I'm going to put it in parentheses because it's a decimal, 1.07 to the x. So again, this is in billions, remember, because we're talking about billions of dollars. And I was in 2005 is where my initial amount started. I want to know 2015. So how many years past? 10. So I'm going to put a 10 And I'm just going to punch it in the calculator. It's going to be 360 times 1.07 to the 10th. So 360 times 1.07 to the 10th is, holy moly, a big number. That's okay. So I'm going to round it to 397.7. I'm rounding it to the 10th. Now, I know I'm talking about money, but this is billions of dollars.
I think you did it.
You think I did it wrong?
Yeah, that's not what I did.
Oh, that's because I did 1.01. I sure did do it wrong. 360 times 1.07 to the 10th. 708, does that sound better? So 708, and I'm going to say $0.2 billion. When we talk about large dollars amount like that, I know that I said money goes to cents, but when we talk about like national debt and these ginormous dollars amount, we always say like 1.2 trillion, which would be 1 trillion, 200 billion, etc. Okay, so just so you know that they do round it with large dollars amount like that. The next application to exponential growth is compound interest. Compound interest is how you can earn a lot of money super fast, dependent on how much you invest. It's also how banks analyze if you take a loan out for a car, they're charging you interest for borrowing you the money, and it's compounded because they want to earn as much money off of you as they can for borrowing it. So compound interest, it works awesome for investing. If you're investing money, because then you earn money off your money. I mean, it just sits there and it keeps getting interest compounded in. Or if you borrow money, if someone lended you money, like student loans, house payments, all that kind of stuff, car payments. Those are all, the bank is compounding that interest, so you're having to pay them on interest you've already, just for borrowing. Here's a weird formula. Notice it does look in the form of y equals a times b to the x. It just looks weird. I don't know if you can read it well. I'm going to a equals p parenthesis 1 plus r over n to the nt. It's the same, it's just much more intricate. So, A is the initial amount, P. B, that growth factor rate, is this inside here. X is just a little bit more intense. It defines what all these variables are. A is your balance at any given time. P is the principal, your initial. R is your interest rate as a decimal. Turn everything to a decimal today. N is the number of times interest is compounded. Here's the, you do need to know these vocab words. You can do semi-annual, you can do annual, I think there's 2 N's. You can do quarterly. Those are the most common vocab words for compounds in finances. Semi means twice a year. Annual means 1 time a year. And quarterly means, what do you think?
4.
Yeah, you got it. Quarterly means 4 times a year. Those are the most common. There's different forms of compounds, but those are the most common. Semi-annual, quarterly. And T is your time in years. Okay, so suppose that when your friend was born, your friend's parents deposited $2,000 in an account that pays 4.5% interest that is compounded quarterly. Now keep in mind, this is just the initial. Maybe they got a bunch of congratulatory money, and they're like, hey, I'm going to take this, I'm just going to throw it into the bank, and didn't touch it. Okay? I want to know, what is the balance going to be when the kid turns 18? So I'm going to go ahead and write all these. P times 1 plus r over n to the nt. I need to figure out all these variables. And it takes a little bit of time to figure it out. P is the initial amount. So P is 2,000. R is your interest rate, 4.5%. Write it as a decimal, 0.045. N is your compounds. So I am compounded quarterly, that means 4. And T is your time in years. It was there for 18 years. Let's figure this out. Then it just gets a little, it's gonna look a little weird, but you can do it. So it's gonna be 2,000 times 1 plus your interest rate over your compounds times your compound times your years. It's so pretty, don't you think? So I'm going to figure out, order of operations tells me I need to figure out this quotient. So in my calculator right now, I'm going to go 0.045 divided by 4. And that's, I like to just punch it all into my calculator. Okay, I'm going to tell you how I'm punching this into my calculator. I'm going to go 0.045 divided by 4. I hit enter, I get a big decimal. I'm going to plus 1, I'm going to hit enter again, and it's still a big decimal. I'm going to raise that to, oops, I forgot, what's 4 times 18? 32, 3, 72. I'm going to raise that to the 72nd power, so to the 72nd, and I get another ginormous number. I'm telling you, these numbers are ginormous. And then I'm going to times it by 2,000.
Wait, how do you times it by 72?
I'll show you. So that is $4,475.53 once you plug that in. Well, but you just earned $2,475 for doing nothing.
You made it sound like
Yeah, I know. But also keep in mind that 2,000, although it might seem like a lot since you're kids, it's not. Imagine if you invested more. The more you invest, the more you make. Now let's suppose that this investment was compounded monthly. Like maybe they found this really awesome deal that was able to compound it monthly for them instead of quarterly. Let's see how much more they would have made. So I still need my P, R, and T. P is my principal. Well, they still deposited $2,000 according to the word problem. R is the interest rate as a decimal, 0.045. N is compounds per year. Now it's monthly, so how many was that? 12. 12 compounds each year. And T is time, 18 years. Now I plug it all into that very crazy formula. So it's going to be 2,000 times 1 plus 0.045 divided by your compounds to the compounds times time. I'm going to just quick figure 12 times 18 out. 216. So this is 216. And then I'm just going to plug it in my calculator again. So it's going to be 2,000 parenthesis 1 plus 0.045 divided by 12 to the 216 is $4,489.01. That doesn't seem like much more. Yeah, because it's not that
it's
much.
like $600.
Yeah, I was thinking it's going to be so much more money, but it's not.
$14.
Okay, so I'm going to choose to stop here and break this up into exponential growth, and then Monday will be exponential decay. So again, exponential growth is it's increasing, and compound interest is also an exponential growth.